So, the first force is called genetic drift. This is a chance event in the gene pool of a small, change in the gene, of a gene pool of a small population due to a chance event. Something happens and it affects the gene pool, especially of a small population. Large populations, like the human population, right? AIDS is I'm not trying to say that AIDS is not significant, but it is. It's a very horrible disease. However, if you look at the human population as a whole, the effect of AIDS on the human population is really just a blip, all right? It does not have a very dramatic effect on the human population as a whole, all right? If you look at the spotted owl, which lives in the Cascade Mountains in Washington State, back in the 80s, there was the volcano Mount St. Helens that blew its top. It threw debris, dust, volcanic ash all over the place. And in that process, there's a very small population of spotted owls. And during that event, not only were some individuals killed, but a lot of their habitat was destroyed. So, which then would kill off the potential kill of other individuals of that species. So, that particular event was very dramatic on the spotted owl. Right, there's two types of genetic drift. There's bottleneck effect, and then there's founder's effect. Bottleneck effect is genetic drift resulting from a disaster. It could be a natural disaster, okay, that dramatically reduces the population size, right? The California elephant seals used to be very, very abundant along the west coast. But in the mid-1800s, gold was found in San Francisco area of California. San Francisco went from a very small town to a large city. It had street lights and people had to have lamps, etc. And you need oil for those lamps to keep your light burning, right? There were these big seals just laying on the beach, very easily could be killed, and they had a lot of blubber, oil. And so they started killing off elephant seals for the blubber until there were very few left. And in one of the acts of environmental legislation, the California Congress enacted a law that banned the killing of elephant seals, and that was before 1900. Now there are elephant seals back on the beaches of the West Coast because of that effort. Founder's effect is genetic drift resulting from a colonization of a new location of a small number of individuals. So, like a pride of lions. The pride population is small. The number of those populations is starting to dwindle because of poaching, etc. And so, when males are born into the pride, they are only kept around long enough to become a threat to the alpha male. At some point in time, those young males will either vie for the alpha male or be kicked out of the pride. And so when those young males are kicked out of the pride, as a part of what they would do is they would sort of hang around the pride, and then eventually one of the males might woo one of the females away from that pride and start a pride of its own. And so when that happens, you're starting a new population that's smaller than the original size, plus you're taking away from that original population. So not only one is very small to begin with, but the other one is even getting smaller. So that can have an effect. Some natural disaster then would have a bigger effect on those populations because they're small. So that's genetic drift. Gene flow is the movement of alleles into and out of a population. So if you move into a population, we call that immigration. I'm emphasizing the I just for your all's sake. Emigration is the movement of alleles out of a population. And so when famine hit Ireland, Irishmen and women, they moved out they immigrated from Ireland and came to the United States, where they immigrated so that they could find a new, better life, right? Immigration is out, immigration's in. Mutation is the change in the organism's DNA, and it creates a new allele, all right? This is extremely rare, all right? It's very, very rare. But it is the source of a lot of genetic variation throughout time and therefore the raw material of evolution. And a lot of this occurs during DNA replication. You know, when we just talked about how the bases are put together, something happens and there's an error in that, the way that they're put together. And when that happens, now there's a different phenotype that arises based on the new DNA arrangement of that gene, right? And things that could cause mutation are things like our mutagens, all right? And they could be physical mutagens, such as high radiation, such as X-rays. It is kind of ironic. You can expose cancer to a tumor and use that to help get rid of cancer. But on the other hand, if you're exposed to high amounts of radiation, you can get cancer, right? Chemical mutagens are chemicals that can cause mutation. One of those is formaldehyde. It's embalming fluid, but it's a preservative used in biology to preserve specimens. It's also a chemical that preserves things like, used to preserve things like toothpaste. Yes, it would clean your gums really good, but it probably wasn't very healthy for your gums, right? Also, they used it to fumigate down. And down, of course, is the soft feathers from ducks used in pillows. And so those fumigated down pillows, you would be sleeping and you would be breathing in formaldehyde. And of course, that's not good, so they stopped doing that as well. But those types of chemicals can cause mutations in the DNA. Non-random mating is a selection of mate other than by chance alone. So you choose your mate, or your mate chooses you, all right? And in most populations, most species, this non-random mating is the norm, except when you're talking like plants and you have pollinators, then the pollen is randomly dispersed versus an animal that chooses its mate. Right? The last thing is the force that we're going to talk about is natural selection. It accounts for most of the morphological and physiological changes that have occurred throughout time within populations. Right. So what is a natural selection? All populations have the reproductive capacity to grow in numbers throughout, throughout a generation, right? But the population size is finite because there are limited resources and space for those individuals of the population. Sooner or later, if something doesn't change, because these are finite, these resources are finite, soon individuals in the population are going to have to compete for those limited resources, right? And so, you can look at farmers. Farmers know how many head of cattle they can get on a particular field, and how long they can have those have them on their fields before they have to change fields. All right. If they don't change their field, or if they add individuals to the population, then at some point in time, the food and the space is going to become an issue, and then individuals of the population then will, of your herd will start to compete against each other for those limited resources. All individuals of the population have the same genes, forming the pool of heritable information. All genes usually have two alleles, but they have two or more alleles, which give rise to different phenotypes. Remember what a phenotype is. What it looks like, what the gene looks like. For instance, you can roll your tongue or you can't. All right. Some phenotypes will be better suited than others for helping individuals compete for those resources, and therefore they have the upper hand in survival and reproduction. So, if you have these head of cattle fenced in and you're not feeding them, supplementally feeding them, and so the grass that's available on this piece of land is becoming less and less, all right? And you have some head of cattle that have longer necks than others, then the longer necked individuals can actually get down and put their neck underneath the fence and eat grass on the other side of the fence. The ones with the shorter necks cannot do this. So those individuals with the longer necks are now better suited for that environment than the short-necked individuals, right? And so that beneficial phenotype, then those with the long necks are now better off to survive. So the ones that are shorter necked then start to get smaller in weight, and eventually, if you just kept it up, they would die off or get less and less of the population. And whereas the long necked ones will survive, and they will reproduce and form long necked babies. All right, and so that particular phenotype then becomes more populous in the population. Genetic changes lead to increase in fitness. This is the contribution of an individual that he makes to the gene pool of the next generation relative to the contribution of other individuals. So what am I providing the next generation that will help them compete for those limited resources with other individuals? So that is the idea of natural selection. There are some phenotypes that provide no benefit whatsoever. They're just there. For instance, your fingertips, all right? They don't provide you a selective advantage over any other individual, right? They're all different, and the only reason we use them right now is to identify people, right? But it does not give me an advantage over anybody else because my fingerprints are different. Whether I can roll my tongue or not, whether I have a widow's peak or unattached or attached earlobes, all those are neutral variations. They don't give me any advantage over other individuals in the population. finally, there are three types of natural selection. So there's one that's called directional selection, is where the number of individuals increase so that one extreme is selected for and the one is selected against and the middle ranges are selected against, right? And we're going to say this is human height, all right? Average human height. All right. And on this axis, we're going to say, let's make it so. And this is time. All right. So in the 1500s, the average height was around 5 feet tall. In the 1700s, it's up to 5.5 feet tall. And we look at 2000, it's at 6 feet tall. This is male human height, right? And you can see that the individuals in the population are getting taller over time. So this is allele frequencies underlying a range of phenotypic variation shift in a constant direction, all right? So you have more individuals now being 6 feet tall than you did back in 1700 when they're 5'5", and in 1500s the average height was 5 feet, right? This example of directional selection, all right? Stabilizing selection is where you have, the mid-ranges selected for, all right, and the extremes, both extremes, selected against. So most of the individuals are in this range, all right? Let's look at human birth weight, all right? This is percent individuals, percent babies, right? 0 to 100, right? All right. And so this is 7 pounds, this is 9 pounds, this is less, this is more, okay? In this frame, most of the individuals are going to be between 7 and 9 pounds when they're born, right? Doesn't mean that if they're born less than 7 pounds or more than 9 pounds that they're going to be frail or die or something's going to happen to them. No, it's just that most of the individuals are born within this birth weight. All right, mine were over on this range. All right, they were above the most frequent, but they're healthy and everybody's doing fine. All right. So this is called stabilizing selection. The last one is called disruptive selection. This is where the extremes are selected for and the mid-ranges are selected against. And the example here is the black-billed seed cracker. It's a bird in South America. The bird is the same species, but some of the birds have a thick bill and some of them have a thin bill. All right. The thick bill is very good at slashing through fruits during the rainy season. The thin bill is more adaptive. It's better at getting seeds from grasses and things like that. All right, during the dry season. And so when a nest is built and eggs are laid, it depends on the whether it's a rainy or dry season, which bill it will have, right? So let's say in the wet season, a nest is built, eggs are born, all right? And since it's the wet season, you would think that the fledglings, when they are born, are going to have a thick bill. But that's not the case. Because as they are born, the parents take care of them, right? So during the wet season, the parents are going to take care of the nestlings. But when they are pushed out of the nest and are out to defend themselves on their own, then it's going to be the dry season. And so when it's dry, what's going to be most available to them? Seeds. And so those individuals who are born in the wet season will actually have a thin bill. Those birds that were born in the dry season, conversely, will be fledged in the wet season, so they will need the big thick bill to allow them to get into fruits more readily. So this is just a way called disruptive selection. And these are the three types. All right. So that concludes chapter 13, and we will start chapter 14 here in a second.